now that we know about functions, we know what is the condition that a function should satisfy, right? If there is a function from set A to set B, we know that every element in A must have an image in B. Okay. Now we have also seen what are real functions, where A and B are subsets of real numbers. So typically, if the A and B are real numbers themselves, we will write it as from R to R. Okay, and it could be some x comma y such that etc. Okay. Now what are some examples of common functions that we are familiar with and that we are going to encounter in this chapter? Okay, the first is polynomial functions. This you are already familiar with. Okay, polynomial functions are functions of the form f of x is equal to a0 plus a1x plus a2x squared and an x power n, where n is any natural number. Now this is something that we have studied about polynomial functions earlier itself, and even how to find the roots of, let's say, a linear polynomial or a quadratic polynomial. Okay. Now what is special about polynomial functions? Well, they are very commonplace, but something that is interesting about polynomial functions is that this function for any a0, a1, a2, etc. and n being natural, you can define this function for every real number. So the domain of polynomial functions is simply the entire real number set, which means there is no value of x that is not allowed for the polynomial function. Every single real number x is allowed for every single value of a0, a1, a2, etc. Okay, that is something very useful when dealing with polynomial functions. Okay, range we don't know because we'll have to actually compute based on the function. Okay, another special function that we will see is the modulus function. Okay, now what is the modulus function? The modulus function takes a number and returns only the positive value. For example, if you have modulus of minus 3.2, it's 3.2. Modulus of 5 on the other hand is simply 5. Now can this be thought of like a regular function from R to R, etc.? Yes. If you take this modulus function, we can say f R to R equals, okay, x comma y such that, now look at this carefully. What this is going to do is, if the number is positive, it will just return that value. If the number is negative, you want to use the negative of that number. Okay. So what kind of ordered pairs will be part of this function? You will have ordered pairs such that y equals x if x is greater than or equal to 0, and y equals minus x if x is less than or equal to 0. All ordered pairs that satisfy these conditions will actually obey this modulus x. Okay. For example, minus 3.2 is a negative number, so it will come under this category. Y must be minus of minus 3.2, so it should be 3.2. This is an ordered pair, that's a part of the modulus function. Then phi comma phi is an ordered pair, that's a part of the modulus function. 0 is included in both categories because plus 0 and minus 0 are both the same, and modulus of 0 is essentially 0. So 0 comma 0 is also part of the modulus function. Now what values are allowed for x in the modulus function? Well, your domain can contain any x value, because any real number you can always compare it with 0. If it's positive, you can take the same number. If it's negative, you can take minus of it. So the domain is, well, we have already written the domain when we said R to R. We should have simply said A to B and then said the domain is real numbers. Okay. All real numbers can be included in the domain, which means mod x function is defined for all real numbers. Okay. Then what about the codomain is all real numbers as is usual for real functions. Now what about the range? What are all the possible y values? You will see that the y values can only be either positive or 0. It can never be negative, because if x is negative, you are already taking minus of that for y. Therefore, the range is the set of positive real numbers, all real numbers greater than or equal to 0. Now this is also denoted using the symbol. This is R, which is the set of real numbers, plus R plus includes only positive real numbers, but to R plus you should also include the number 0, because 0 is also allowed in the range. So even though the domain is all possible real numbers, the range only has R plus and 0. Okay, so this is another special function. Now a third special function is denoted by square bracket x. This is called greatest integer function. And what does the greatest integer function do? The greatest integer function returns the greatest integer less than or equal to a given number. For example, if I want to find the greatest integer of 7.43, what is the greatest integer less than this? It's equal to 7. But suppose I want to find the greatest integer of minus 2.8. Okay. Now think of the greatest integer less than this number. Now look at some integers less than minus 2.8. On the number line, this is 0, minus 2 will be here, and you will find that if minus 3 is here, minus 2.8 is something here. Now all numbers less than minus 2.8 will be to the left of minus 2.8, which means numbers like minus 3, minus 4, minus 5, etc. Now among all those numbers, which is the biggest, which is the greatest integer? The greatest integer less than minus 2.8 is simply minus 3. So what does greatest integer function give? It gives you the greatest integer less than or equal to x, which means greatest integer of, let's say, minus 5 is simply minus 5, because it can be equal. Greatest integer of 6 is 6. Greatest integer of 0 is 0. Okay. Now what is the domain of the greatest integer function? What values can you put into x? Well, any real number is allowed, whether positive, negative, rational, irrational, etc., because you can always find out if that number is an integer or not an integer, and either way it's defined. If it's an integer, you directly return that number. If it is not an integer, then find the integer that is greatest integer but less than the given number. That's all. So that means the domain is again all possible real numbers. The range can only be integers. So we can just denote it using the sometimes I is used, sometimes z is used. Okay, I, suppose we use the symbol I to denote the set of all integers, then the range can only be I, but the domain is the set of all real numbers. One other idea that we need to know when we learn about functions is operations on functions. So let's say we have a function f of x and a function g of x. Can we ask questions like, what is f plus g of x. Okay, this is adding two functions. So this is a new function, we can call it h. We can say h of x is f plus g of x. But what is f plus g of x? This is nothing but f of x plus g of x. So this is the sum of two functions, okay, whose result is essentially the sum of f of x and g of x. Now similarly we can write f minus g of x is f of x minus g of x. fg of x is f of x times g of x. Okay, now it's quite clear that we are just directly doing the same operation. There's no big restriction. There's also another thing called alpha f of x, where alpha is some scalar which is a real number. So this is alpha times f of x. These are all quite trivial in terms of relations. Like for example, what this says is, if you have f of x is 3x squared plus 2 and g of x is, so let's say f of x is 3x squared plus 2 and g of x is, let's say, mod of x plus 5, f minus g of x is simply f of x minus g of x, which is 3x squared plus 2 minus mod of x plus 5. Just directly subtract. Okay, so it's quite straightforward in terms of operations, whether it's plus or minus or multiplying the functions or multiplying by a scalar. Now what can we say about the domain of these new functions, f plus g, f minus g, fg, etc.? What would be the domain of these functions? Well, it's quite simple. Wherever both f and g are defined, these composite functions that are obtained by doing these operations, f plus g, f minus g, fg, etc., or alpha f, all of these functions will be defined wherever both f and g are defined. The only exception is if you do a ratio f by g of x, then this is f of x by g of x, where, but this is subject to g of x not being 0. Please understand that you can define the quotient of two functions only if the denominator is, or the a ratio of two functions only if the denominator is not 0. So this is one thing to keep in mind. The domain of this function is not wherever f and g are defined, it is wherever f and g are defined and where g of x is not equal to 0, because division by 0 is not allowed. This is one thing that we need to keep in mind when we have some basic operations on functions. Okay, so since we know this, we can also now look at how do we find the domain of what are known as rational functions. Rational functions of the form f of x is equal to, let's say, p1 of x by p2 of x, where p1 and p2 are polynomials. Okay, so how would you find the domain of this function? Well, the domain of all polynomial functions we know is real numbers. So it's r minus all real numbers. But what should you take away? What you should take away is all the values that will make p2 of x 0, minus, we can say, the set x such that p2 of x equals 0. If you subtract this set from the set of all real numbers, all the remaining values will be allowed and valid for the domain of f of x. Okay. Another category of functions that we need to be familiar with are trigonometric functions. So trigonometric functions are functions of the form sin x, cos x, tan x, secant x, cosecant x, cot x. Okay, Now, for each of these functions, we can actually find what could be the domain, range, etc. Let's just have a very brief understanding. If you want to discuss these functions in detail, then that will be in a different chapter. Okay. Now here, let's take sin x. Okay. Now we know that sin x is a function that can be defined for all values of x. You can start from x equals 0, go till pi by 2. This is pi, 3 pi by 2 and 2 pi, and then again you can go all over again for values bigger than 2 pi. So here, so the domain is simply all possible real numbers. Okay. And what is the range? The range is only values from -1 to 1. Cos x, again domain is all real numbers, range is from -1 to 1. Now what about tan x? Okay, tan x is, you can think of it as sin x by cos x. Therefore, when is tan x not defined? Well, sin x is defined for all real numbers, cos x is defined for all real numbers. So when is tan x not defined? When cos x is 0. So the domain is all real numbers minus those values which will make cos x is equal to 0. Now cos x equals 0 at, let's say, pi by 2, okay, and 3 pi by 2, etc. So these are all values. You can write it in some general form, but you have to understand that at these values tan x is undefined. Similarly, we can write for cot x, secant x, cosecant x, etc. Now the range for tan x will be -infinity to infinity. Tan x can take all possible real values. So if we know for sin x, cos x and tan x, then we can use this information for the other trigonometric functions. Of course, a detailed understanding of each of these functions with its graphs is part of the trigonometry section, but here just the basics of these trigonometric functions we want to understand to find domain, range, etc.